Hello, everyone. My name is Dario, and I'm a PhD candidate in the systems group at ETH Zurich. I'll be presenting Farview. Farview is, first of all, an open research platform designed to explore disaggregated memory solutions in modern database systems. Now, the platform is implemented as an FPGA-based SmartNIC, making DRAM available as a pool of network-attached memory accessible over RDMA. One additional feature of the Farview is the capability to perform line rate data processing with minimal overheads. So from the database perspective, Farview acts as a disaggregated buffer pool with operator pushdown capabilities that is byte addressable by the threads running queries in the compute nodes. So what motivated us to design the Farview? Well, one of the main bottlenecks databases need to overcome is I/O overheads. And although we do have faster storage in modern days, we have SSDs, NVMEs, the I/O overheads still remain one of the major factors in the overall performance. Now, to minimize these overheads, databases tend to keep more and more data in local fast DRAM memory in compute nodes. This approach, however, does have its downsides. Firstly, it induces excessive data movement and extra copies of the data. As an example of this, optimized query plans typically push down certain operators like projections or selections, which often filter out large portions of the data. And even though this is the case, in traditional approaches, data still has to be shipped all the way to the compute nodes and then processed there fully. This additional movement has a direct negative impact on performance and memory requirements. Now, secondly, memory capacity is also a limitation. DRAM is expensive, and provisioning it independently for every node can be quite costly and difficult. An alternative approach is to exploit the distributed nature of the databases, especially in the cloud environments. Now, in such cloud settings, it is very beneficial to disaggregate the resources, which can allow us to independently provision each of them. This approach is quite popular in modern cloud architecture, where there is a tendency towards disaggregation of compute and storage. The step that we're proposing in Farview is to additionally disaggregate compute and memory as well. And this is something that is being quite actively pursued in research in various forms, as either disaggregated DRAM, disaggregated persistent memory, which might also be an interesting target for Farview, FAR memory, smart remote memory, and so on. So it does seem to be a trending topic currently. Now, we position the Farview to make the most of disaggregated memory to address the issues of inefficient data movement and memory capacity. We do this by provisioning the memory for query processing nodes on demand and by offloading certain portions of the processing directly to the Farview nodes. Now, to showcase the advantages of this approach, consider, for instance, the following two queries. Both of them can, for example, read large amounts of data just to discard the most of it. In traditional architectures, all required tables would still have to be copied all the way to the compute nodes for processing. In Farview, on the other hand, we reduce the memory requirements and data movement by centralizing the buffer cache in disaggregated memory and by pushing down these selection and projection operators so the compute nodes receive only the relevant data. Now, the processing is done directly on the data streams, simultaneously with the data being read from the memory and sent to the network. And importantly, the impact of this additional processing on the overall performance is negligible. Now, to accentuate this point, we compare a case where we're not doing any processing in the Farview, so we're just performing a simple read with a basic RDMA read operation, to a case where we're performing an additional AES decryption on the same data as it is being read. Now, as the encryption operator is highly parallelized and fully pipelined, it is able to easily sustain the network line rate. The added latency of this operator is also small in comparison to the network and memory operations. And this means that this decryption is very nicely hidden behind these other operations. And this can be seen in the figure here, where the performance is virtually the same, even though in the second case, we are performing some meaningful work as well. All of the operators in the Farview are implemented in the same fashion, so effectively the processing in Farview is functioning as a bump in the wire between the memory and high-performance network. Now, prototyping a smart disaggregated memory requires several components, and modern FPGAs are a natural match for such functionality, as high performance and flexibility can both be combined in a single device. They also support high performance networking and can have substantial amounts of local memory being attached with heaps of bandwidth. For these reasons, the Farview is implemented on a modern FPGA data center card, and the architecture is organized around three distinct modules: the operator, the memory, and the network stacks. These stacks are connected via high-performance buses, so there are no additional bottlenecks being introduced along the way. Now, to deploy operators that can process the data, the operator stack is divided into multiple isolated dynamic regions that operate concurrently. Clients access the disaggregated memory by first opening a connection to one of these dynamic regions. And each dynamic region can then serve query requests and can be loaded with one of the available operator pipelines that can execute a set of different queries. Now, importantly, the operator pipelines in these regions can be swapped on the fly during runtime without affecting the integrity or operation of other dynamic regions. And this is what gives Farview a much needed flexibility in comparison to traditional in-memory database accelerators. Now, an operator pipeline can contain one or more operators that provide partial query processing. As done in conventional query processing, operator pipelines are constructed from individual blocks, which are implementing a given operator and provide a standard interface to combine them into pipelines. Farview currently supports a range of operators, including projection operators that can reduce the number of returned columns, selection operators that can filter the data according to a collection of predicates and greatly reduce the amount of data ultimately sent over the network, grouping operators that combine tuples and can perform aggregation, for instance, and these operators are actually using hashing, which can be quite efficient in FPGAs. And then finally, system operators that can perform some additional processing on the data, for example, the encryption operator that we've shown that can be used to enforce security measures, which can be very important in disaggregated systems. Now, the modular nature of these pipelines and the reconfigurability of the FPGAs allows the list of these operators to be easily extended at any point. The memory stack implements the actual buffer pool using the onboard DRAM attached to the FPGA. It handles all memory allocations, address translations, and concurrent accesses from dynamic regions. The memory is organized into multiple channels, and the memory management unit in Farview uses an interleaving abstraction to aggregate the bandwidth by accessing all these channels simultaneously and by allocating the memory in a stripe pattern across all available channels. And this allows us to take advantage of full memory bandwidth, which is very useful, especially in filtering applications, which can discard a lot of data and where we can process this data at higher rates than the available network bandwidth. This can reduce the overall response times directly. Now, this is something that would not be possible if the memory channels were not directly exposed to the Farview and if they were accessed over a PCIe, for instance, as is often the case. Now, the network stack manages all external connections and requests for all concurrent accesses. The network stack supports RoCE v2 at 100 gigabits using the open source network stack developed in our group. The stack is extended with out-of-order execution and fair sharing to support multiple dynamic regions. And we also add a special Farview verb based on InfiniBand send to issue efficient query requests directly through a high-performance network fabric. The underlying transfer protocol for this verb does not change, which makes Farview compatible with commercial InfiniBand cards. Now, the logic in the operator stack reacts directly to these requests without them being written to memory, which is one of the reasons why Farview has quite low latencies comparable to regular one-sided RDMA verbs. In terms of programming, Farview exposes a simple high-level data API covering both the critical path operations and connection management operations. The data API is written in C++, but other front ends can be used as well. And it is intended to be used by the query compiler in Farview rather than directly by the client. And the development of this dedicated query compiler is the next target for the Farview project. Now, for evaluation, we compare Farview's smart disaggregated buffer pool with two different baselines, a buffer cache implemented in local memory where the processing is done on the local general purpose CPU, and a remote buffer cache similar to Farview but without the FPGA and implemented on the memory of a different machine reachable through a commercial Mellanox NIC via RDMA operations. Now, this latter configuration resembles what is being done today for storage, where part of the processing is moved to a CPU located in the storage server. It also matches the definition of a remote memory proposed in the literature. And we compare the effectiveness of each operator implemented in the Farview. And for instance, in case of selection operators, Farview outperforms both of the baselines in all cases and for different selectivities, owing that to very cheap selection and very high filtering throughput that we can perform in the FPGA. A similar story is in the cases of grouping operators and regular expression matching. where the advantage of the Farview scales drastically as the data size increases. And this is due to some of the operations in these operators that can be very expensive to execute on the CPU. We also perform a test for multiple concurrent clients where the Farview performance advantage remains due to fully parallelized dynamic regions. Now, to conclude, Farview implements a research platform which helps address the capacity limitations and data movement inefficiencies through the use of RDMA, reconfigurable hardware, and disaggregated memory. It is competitive with traditional non-disaggregated local buffer cache solutions and outperforms them in a number of use cases, showing that smart disaggregated memory might be a viable alternative in modern cloud environments. Finally, we would like to thank Xilinx for the donation of the XACC cluster, which we use to develop Farview. And thank you all for listening. And if you have any questions, feel free to contact us at any point.